Hello everyone, welcome to my channel Lifescience with Nivedita. So this is KSET Lifescience 2023 most important topics discussion series part 5. So the videos of previous part, that is 4 parts, link I provide in the description. Just kindly check it out. Okay, so in today's video we're going to discuss about the most important topic, that is from the population genetics. It is Hardy-Weinberg equilibrium. So if you check the previous year question paper, there is a one question from this population genetics, that too from this Hardy-Weinberg equilibrium, a very important topic. So several problems are coming under this particular topic, so we will solve problem also. Okay, so by solving the problem we discuss this Hardy-Weinberg equilibrium also. Okay, so now without any further delay we just start it. So first of all, what is this Hardy-Weinberg equilibrium or Hardy-Weinberg principle? Okay, so here you can see this principle, which one, the Hardy-Weinberg principle will says that allele frequencies in a population is constant from generation to generation. So this principle says, which one, Hardy-Weinberg principle will says that allele frequencies in a population is constant, that is in a constant from one generation to another generation. The frequencies of a different alleles and genotypes within a population will remain constant throughout the time, as long as there is no evolutionary influences is present. So when allele frequencies in a population is constant means what? There is no evolutionary influences is present. There is no mutation, right? When there is no mutation takes place from generation to generation, the allele frequency is constant. That is what the Hardy-Weinberg principle will explain. Okay, the sum total of all allelic frequencies is equal to 1. So this is what is Hardy-Weinberg principle will say, that is the sum total of all the allelic frequencies. If there is one allele, if there is two allele, if there is three allele, okay, the sum total of all these allelic frequencies is equals to 1. Okay, so it is one equation is there, so that we discuss. So there are some assumptions are there of this Hardy-Weinberg equilibrium. That is, assumptions of this Hardy-Weinberg equilibrium are: when there is a no selection, when there is a no mutation, when there is no migration. Okay, so when there is no mutation, migration, selection are there, that is what, which will leads to the constant allelic frequency. Okay, so next, when there is a large population and also random mating, that is also leads to a constant allelic frequency from one generation to another generation. This is what, that is, these all are the assumption of Hardy-Weinberg equilibrium. So based on this assumption, they will find out one equation to calculate the genotype frequency with help of allelic frequency. Okay, so now, so this is what the Hardy-Weinberg equilibrium says. So here two alleles are there, P plus Q is equal to 1. So allele 1 is there, this will represent P plus Q, and allele 2 is there, so that will represent P plus Q. So to find out the genomic frequency, that is, which is equals to the 1, that is P plus Q is equal to 1. This is for one allele. If there is two alleles are there, so P plus Q and P plus Q is equal to 1. So first of all, what is this P and Q and all? So I think you may get confused. So here this P represents frequency of the dominant allele, and this Q represent frequency of the recessive allele. If if there is a triad is there in a population, triad means what? It's characters. If which one, the pea plant, okay, the Mendel's experiment. So in a pea plant there are two alleles are there. One is the tall, another one is the dwarf. This is what, this is a triad, one character. Okay, in a population, triad is a character. So in that characters, two alleles are there, that is dominant allele and also recessive allele. So here tall is a dominant allele and dwarf is a recessive allele. Okay, so here this P, we can say this P is a tall because it is a frequency of dominant allele, and here Q is there, that is dwarf, that is a frequency of recessive allele. Okay, so here where P plus Q, frequency of dominant allele and frequency of recessive allele is equals to 1, because this Hardy-Weinberg will says it is a constant from one generation to another generation. Okay, so now you can see this is what the allelic frequencies can be used to determine the genotype frequency. So to find out the genotype frequencies, these allelic frequencies will help. So I already mentioned this P represents frequency of allele A. A means what? That is dominant allele. Okay, and Q represents the frequency of recessive small a, that is recessive allele in a population, because in a populations both dominant alleles are also there, recessive alleles are also there. We have to find out both dominant and recessive in the case of genotype frequencies. Okay, so if there are only two alleles, P plus Q is equal to 1. If there are three alleles are there, in that case P plus Q plus R is equal to 1. Okay, in the case of two alleles, P plus Q is equal to 1. In the case of three alleles, P plus Q plus R is equal to 1. Okay, so with the help of this P plus Q, they identify one equation to find out the genotype frequencies. So how they identify? So here you can see P plus Q, this is a allele 1, and here again P plus Q, that is allele 2. So here it is equals to 1. Okay, so again to find out this equation, P plus Q is equal to this multiplication. Okay, P plus Q. So P into P square. So P into Q, PQ. Again P into Q, that is PQ. Okay, so that is QP. So next one, Q into Q, that is Q square. So P square, here one PQ, here one PQ, that is 2PQ, and this one is Q square. So with the help of these two alleles, Hardy-Weinberg will find out the equation to find out the genotype frequencies. So now this P square will represent the frequency of dominant allele, and this Q square will represent the frequency of recessive allele, and this 2PQ, what is this? This 2PQ will helps to identify the heterozygous dominant. Heterozygous dominant. So for example, I'll just take three alleles, A and small a, 2 small a. Okay, so this capital 2A will represent homozygous dominant. So this homozygous dominant, that is P square, and this small 2A are there, right? So this is homozygous recessive, that is Q square. Homozygous recessive, homozygous dominant, but this 2PQ is there, right? So this one is what? That is big A and also small a, that is heterozygous dominant. Okay, phenotypically it is showing a dominant character, but this is a heterozygous. Okay, one gene from the dominant character, another gene will from the recessive character. Okay, so this is about this Hardy-Weinberg and also its equilibrium. Okay, so some problems also we discussed. Then it is easy to understand this equation and also about this Hardy-Weinberg equilibrium. Okay, so see the same thing what we discussed right now, that is P square plus 2PQ is equal to Q square. So P square means what? Frequency of homozygous dominant genotype, and 2PQ is frequency of heterozygous genotype, and Q square is a frequency of homozygous recessive genotype. Okay, so next this is a Punnett square of this Hardy-Weinberg equilibrium. You can see this will represent what? A and A, that is homozygous dominant, and this is heterozygous dominant, and this is also heterozygous dominant, and here homozygous recessive. P square 2PQ plus P square. Okay, with the help of this Punnett square, we can identify genotype frequencies. P square plus 2 PQ plus Q square is equal to 1. This is what Hardy-Weinberg equilibrium. Very, very important. Okay. So next. So this is the graph of Hardy-Weinberg equilibrium. So this blue color is there, right? So that will indicate the homozygous recessive. You can see here small a is there, right? So this blue line indicates homozygous recessive. Which one homozygous recessive? That is Q square. Okay. And here this green color will represent heterozygous dominant. Which one is heterozygous dominant? That is 2PQ. You can see. So gradually it is increasing, but at some point what happened? It will reach some point and then again it is decreasing. But this homozygous recessive, gradually it is in the higher condition, but you can see then later on it will decrease. But you can see this red color will represent what? That is homozygous dominant, that is P square. So initially it is in the low frequency, but again you can see PQ frequency, it is increased. Okay, so this is the graph of Hardy-Weinberg equilibrium, that is homozygous recessive, homozygous dominant, as well as heterozygous dominant. Okay, so this graph will easily says the allele frequencies of P square, Q square, as well as 2PQ. Okay. So next we'll solve some problems so that people get an idea regarding this Hardy-Weinberg equilibrium. So just go with the problems. So first problem here, okay, in a Caucasian population of the US, 1 in 2,500 babies is affected by a recessive condition, that is cystic fibrosis. This is a recessive condition disease. Which one? Sorry. That is cystic fibrosis. Okay. So here in this population, the frequency of the dominant allele is. So here they are given the recessive population. So with the help of this recessive population, we have to find out the frequency of dominant allele. Very easy. Okay. So first here, already they have given the recessive condition, right? So what is that? The recessive condition. So recessive means what? So here formula is there, P square plus 2PQ plus Q square is equal to 1. This is what the Hardy-Weinberg equilibrium equation. So Q square is what? That is for homozygous recessive, and P square is homozygous dominant, and 2PQ is for homozygous. Oh, sorry, I think it is. Okay, correct. Okay, so this is what? That is heterozygous dominant. This is homozygous recessive. Okay, so now with the help of this equation, we can find out the frequency of dominant allele. Okay, so first Q square is what? That is frequency of recessive allele. They already given in the question, that is 1 in 2,500 babies is affected by a recessive condition. So here Q square is equal to 1 in 2,500. So 1 divided by 2,500 is equal to 0.0004. Okay, you can calculate yourselves with the help of calci. So next, with the help of this Q square, it is easy to find out Q. Okay, so here already Q square we have, that is 0.004. So Q is equal to square root of Q square. Okay, so that is square root of 0.0004. That is Q is equal to 0.02. Okay, so now we got Q, that is Q is equal to 0.02. Okay, so now with the help of this Q, we can easily identify P. That is P, just take different color, it is easy to differentiate. Okay. Okay. So P plus Q is equal to 1. We know for the allele 1, that is P plus Q is equal to 1. So here already we know the Q value, right? So now we have to find out the P value. That's why P is equal to 1 minus Q. So what is the value of Q? 1 minus 0.02. Okay, so 1 minus 0.02, that is 0.98. That is the value of P. P is what? That is 0.98. So now P is there. So now how to find out P score? Just square the P, this P. Okay, so P square is equal to 0.98 into 0.98. That is somehow coming 0.960 like that. So just write down 0.96. Okay, so Q is 0.02, P is 0.98, and Q square is what? That is 0.004 is the Q square, and 0.96 is the P square. 0.96 is the P square. So now we have P square, we have P square, we have Q square. Okay, so now just apply these values to this equation. That's it. Already we have P and Q also. Okay, so now apply to this values to the formula. What is the equation? P square plus 2PQ. So already we got the answer. Because of this, to find out the 1, we have to substitute the values to this equation plus Q square. Because the 1 is there, right? It has to come 1. If there is no, 1, if there is no 1 means that represents your problem is wrong. That's why. So P square is what? That is 0.96, and 2PQ means 2 into 0.98 into 0.02, that is Q, and plus Q square is what? That is, you can see here, Q square is 0.0004. Okay, so when we calculate, when we add all these things, we get 1. So this indicates what? Your problem is right. The substitution and also the Q square, P square value, everything is correct. Okay, so what they are asking in the question? They asked, find out the frequency of dominant allele. So here, what is the dominant allele? Which one? That is P square is the dominant allele. So already we have the value of the P square. So the dominant, one of the dominant allele is what? That is P, and the value of P is what? That is 0.98. Okay, so answer for this question is the option D, that is 0.98 is the frequency of dominant allele. Okay, so clear? So like this you have to calculate. It is very, very easy. Okay, so if you know this equation and also substitution thing, then it will be very easy. Okay, so now just move on to the next question. Just Hardy-Weinberg equivalent questions only, because if you check the previous year questions, just problems only they asked. Okay, so that's why just solving some questions. So here, what is the next question? Yeah, a sample A population has 36% of homozygous recessive genotype, that is small a and A. Then the frequency of allele A is what? Okay, so here they are giving the A square genotype, recessive genotype AA, right? That is small AA they have given, that is recessive type. We can say this is a Q square. How much percentage? That is 36%. So then we have to find out the frequency of A. So now we have to find out Q. Very easy. Okay, so here Q square is equal to, percentage means what? 100, right? That is 36 divided by 100. So that will 0.36. Okay, so next, that is with help of this Q square, we can easily identify the Q. Q is equal to square root of Q square, that is square root of 0.36. So 0.36 is 0.6. So here 0.6 means what? That is A, allele A. So in the percentage, that is 60%. It is very easy. So So the frequency of allele A, that is small q, is what? That is 60%. Option C is the correct answer for this question. Okay, so now move on to the next question. That is next problem. Okay, so 360 out of 1000 individuals in a population have a genotype of AA, that is dominant, P square, while 480 have AA. So here already they have given the dominant, heterozygous dominant, 360 out of 1000, that is homozygous dominant, 480 have heterozygous dominant genotype. The rest 160 belongs to small a and a, that is homozygous recessive. Okay, so they are given all alleles, that is genotypes. So now we have to identify the frequency of allele A in this population. So just substitute everything. So dominant, homozygous dominant, that is P square. Sorry. What is the value of P square? Already they have given 360 out of 1000. So 360 out of 1000, how much? That is 0.36. Okay, so then heterozygous dominant, that is 2PQ, 480 divided by 1000. So 480 divided by 1000. So next, homozygous recessive, that is Q square, 160 divided by 1000. You just calculate yourself, because in this question they just asked big A, so that's why this P square is enough to calculate this big A. Okay, so here P square is there. P square is equal to 0.36. To find out the P, what? That is P is equal to square root of P square. So square root of P square means that is square root of 0.36. So square root of 0.36, that is 0.6. So the frequency of allele A, the frequency of allele A in a population is 0.6. So option B is the correct answer for this question. So like this, you have to calculate the frequency of homozygous recessive, that is A, P, Q, 2PQ, like this. It is very easy. But the one thing is, if people know which one, Hardy-Weinberg equilibrium. That's it. Okay. So next question, a gene. Oh, sorry, 1 second. Okay. Okay. So a gene locus has two alleles, that is big A and small a. If the frequency of dominant allele A is 0.4, then the frequency of homozygous dominant, heterozygous, and homozygous recessive individuals in the population. Okay, so they just given A. For example, if P square is there, only P value they have given. So with the help of this P value, we have to identify homozygous dominant, heterozygous dominant, as well as homozygous recessive. So very easy. So how to calculate, you can see here. So what they have given, so just write down what they are already given in this question. Okay, so already they have given, that is big A, that is 0.4. Okay, so here this A represents P, right? Okay, so here P is 0.4. Just square this. P square is what? That is 0.16. P square is what? That is 0.16. So P square represents what? Homozygous dominant, right? So this P square will represent capital A and A. Okay. So next, with the help of this P, it is easy to calculate Q. That is P plus Q is equal to 1. So Q is Q is equal to 1 minus So 1 minus P is 0.4. So 1 minus 0.4, that is 0.6. Okay, so Q is 0.6 and Q square is what? That is 0.36. This is Q square. Okay, so here already P is there. Let me take some other color so that it's easy to identify. So P is 0.4 and Q is 0.6. Okay, and Q square is 0.36 and P square is 0.16. So here already P square is there, Q square is there, and P and Q also there. It is easy to calculate 2PQ, that is heterozygous dominant. Okay, so 2 into what is the value of P, that is 0.4, and what is the value of Q, that is 0.6. So 2 into 0.4 into 0.6, that is 0.48. Okay, so now everything is there. 2PQ is there, P square is there, Q square is there. So highlight this thing. So 2PQ value is what? That is 0.48. So just substitute everything to the formula. What's the formula? P square plus 2PQ and plus Q square is equal to 1. Okay, so what is the P square? 0.16. What is the 2PQ? 0.48. What is the Q square? 0.36. So if we add these three things, we will get 1. Okay, so just compare this thing, that is compare this equation and also the options. So option A, you can see 0.16, that is P square, correct. 0.48, that is 2PQ, correct. And 0.36, that is Q square, correct. So option A is the correct answer. So this A represents P square, this small a represents Q square, and this represents 2PQ. So option A is the correct answer. Okay, so that's fine. So this is how you have to calculate. Very easy, right? So I feel very easy this Hardy-Weinberg equilibrium. So initially, before knowing this Hardy-Weinberg thing, I was also thinking, oh, these problems, anyhow, math is there, no. I'm very far from maths, that's why. But it is very easy. Okay. So the last question of this video. So what does P square in the below mentioned Hardy-Weinberg equilibrium indicate? Anyhow, you people know, right? So what is P square? That is homozygous dominant. So which option is correct? Option C is correct. Individuals that are homozygous dominant is P square. So individuals that are heterozygous dominant is 2PQ. So individuals that are homozygous recessive is Q square. Individual having a lethal gene. So this is not option. Okay, so option C is the correct answer. So here what they ask, that is P square. P square indicates homozygous dominant. So this is about Hardy-Weinberg equilibrium and also some problems. I hope this video will help to learn this Hardy-Weinberg thing. So if you like this video, hit the like button and share with your friends and subscribe to my channel for more videos like this. And then your comments, your like will motivate me to do more videos like this. Okay, so thank you so much for watching. Subscribe to my channel.